The Milky Way. The very name sounds like a promise of mystery, a whisper of something both infinitely distant and intimately familiar. On a moonless night, we can see its silver arc stretched across the heavens, as if someone had spilled milk through the sky, leaving behind a shining trail of countless stars. This is our galaxy, our cosmic home, so vast that the human mind struggles to grasp its true scale. Inside this immense structure hide facts and patterns that defy imagination. Imagine opening a textbook of nature, but one written not in ink, but in starlight and clouds of cosmic dust. Each fact is like a page, each star like a letter in this great book. And the more we read, the more we realize the Milky Way is not merely a collection of stars, but a living system, dynamic, ever-changing, and majestic. Its size alone overwhelms. The diameter of our galaxy is about 100,000 light-years. Light itself, racing at nearly 300,000 kilometers per second, takes 100,000 years to cross from one side to the other. Which means if we gaze toward the edge of the Milky Way, we are seeing it not as it is now, but as it was when Earth had not yet known the first steps of humankind. Within this colossal disk exist somewhere between 100 and 400 billion stars. Each one is a sun in its own right. Each may host its own system of planets, moons, asteroids, and comets. Together, they form a cosmic metropolis, where stars are the houses and nebulae and clusters are the parks and plazas. We do not live in an empty desert, but in a vibrant, bustling city of worlds. Yet we can never see the Milky Way in its entirety. From inside, it appears to us as a luminous band across the sky. Only if we could step outside would we behold its true form. A grand spiral, its arms curling gracefully like the strokes of a painter's brush. Our solar system lies in a quiet suburb of this galactic city, nestled within the Orion Arm, far from the bright and violent center. At that center lurks one of the galaxy's greatest wonders, a supermassive black hole known as Sagittarius A-. With a mass equal to millions of suns, it anchors the Milky Way in its gravitational grip. Stars near it race at speeds so great they complete full orbits in mere decades. By contrast, our own solar system takes 200 million years to make just one lap around the galactic core. In the entire age of dinosaurs, Earth circled the galaxy only a handful of times. But the Milky Way is not built of stars alone. Great clouds of gas and dust drift through it, serving as the wombs of future suns. Invisible to our eyes, these cold clouds slowly condense under gravity until, at last, fusion ignites and a new star is born. What seems like eternity to us is just a heartbeat in galactic time. In recent decades, astronomers discovered that nearly every star may be accompanied by planets. Billions upon billions of worlds, many Earth-like, some within the gentle habitable zone where liquid water could flow. Our galaxy is like a vast neighborhood where every house shelters hidden rooms, each a stage upon which life could one day emerge. And then there's the mystery of mass. The Milky Way's true weight is close to 1 trillion suns, but most of it is invisible. Astronomers call it dark matter, a silent, unseen framework that holds the galaxy together. We cannot see it, yet its gravitational hand shapes the paths of stars, guiding them like actors moving to lines in a script written backstage. Even the galaxy itself is moving. The Milky Way hurtles through space at hundreds of kilometers per second, pulled toward its neighbor, the Andromeda Galaxy. In about 4 billion years, the two will collide and merge, forming one colossal, elliptical galaxy. To us, it seems a distant and unimaginable event, yet to the universe it is but another step in an endless dance. Every moment, dramas unfold in this galactic city. Stars are born, stars die. Supernovae erupt, scattering heavy elements, carbon, oxygen, iron, into space. Those same atoms later form new stars, new planets, and eventually living beings. The calcium in our bones, the iron in our blood, the oxygen we breathe, All were forged in the fiery hearts of ancient stars. We are quite literally children of the Milky Way. And this is only the beginning. We have barely turned the first few pages of the story. Beyond lies a universe of wonders. Globular clusters glittering like swarms of bees, streams of stars torn from satellite galaxies, pulsars ticking like cosmic clocks, red giants swelling to monstrous sizes before fading into white dwarfs. Step by step, fact by fact, the Milky Way reveals itself. A grand puzzle whose completed picture is nothing less than the story of existence itself. The Milky Way is not just a spiral disk of stars. It is layered like a cosmic onion. Beyond the thin, bright disk that we see stretched across the night sky lies a thicker disk, a spheroidal halo, and streams of stars pulled from smaller galaxies. These structures are faint and ghostly, yet they reveal the true complexity of our home. The halo, for instance, is sprinkled with ancient globular clusters, dense, spherical gatherings of hundreds of thousands of stars, bound tightly together for billions of years. They orbit the galaxy like bees swarming around a hive, relics from the Milky Way's earliest days. At the heart of these clusters, stars are crammed so closely that if Earth were located there, the night sky would never know darkness. Hundreds of suns would blaze overhead, casting their light bright enough to read by. These ancient swarms remind us that the Milky Way was not born as a finished spiral. It grew, fed by collisions and mergers, swallowing smaller galaxies over eons. Even today, stellar streams, faint rivers of stars, reveal the ghosts of galaxies long consumed. Their remains stretched and scattered by gravity. Among the most striking features of our galaxy are the spiral arms themselves. They are not rigid structures, but waves of density, like traffic jams on a cosmic highway. Stars move in and out of them, but the pattern persists, a ripple carved into the disk. Within these arms, stars are born in vast nurseries, nebulae where hydrogen glows pink and blue under the light of newborn suns. The Orion Nebula, visible even to backyard telescopes, is but a tiny example of the colossal stellar factories that dot our galaxy. Not all stars are solitary like our sun. In fact, most belong to multiple star systems. Binary stars, two suns locked in a gravitational embrace, are common. Some whirl around each other in tight orbits, while others drift so far apart they seem barely connected. Imagine a world where two suns rise each morning, casting twin shadows across alien landscapes. The Milky Way contains countless such systems, each a stage for exotic skies. Then there are pulsars, the dense, collapsed cores of massive stars that exploded as supernovae. These neutron stars spin with unimaginable speed, some hundreds of times per second, beaming radio waves like lighthouses in the cosmic night. To us, they appear as regular pulses, precise as clockwork, unyielding across millennia. These cosmic metronomes have become tools for astronomers, allowing us to map the galaxy and even test the very fabric of space-time. The Milky Way also brims with extremes. Red supergiants swell to hundreds of times the size of the Sun, their outer layers tenuously held, destined to be cast off in fiery death. White dwarfs, by contrast, are stars the size of Earth, but with masses close to that of the Sun, so dense that a teaspoon of their matter would outweigh mountains. Black holes, both stellar and supermassive, hide in the shadows, invisible but powerful, warping the orbits of anything nearby. Surrounding all of this is the mysterious medium of interstellar space. Far from empty, it is filled with tenuous gas, dust grains, magnetic fields, and cosmic rays. Invisible to human eyes, these threads weave the galaxy together, carrying signals of past explosions and sculpting the conditions for future starbirth. Astronomers have found giant bubbles blown into this medium by supernovae, cavities tens of light years wide, as if the galaxy itself were breathing in and out. And then there is the Milky Way's relationship with its companions. Our galaxy is not alone. Dozens of smaller dwarf galaxies orbit it like satellites around a planet. Some are so faint they were only discovered in recent years. The Magellanic Clouds, visible in southern skies, are the largest and brightest of these companions, each a galaxy in its own right, tugged and distorted by our gravitational pull. These companions remind us that galaxies are not isolated islands, but members of a larger cosmic archipelago, forever interacting, exchanging stars, and reshaping one another. The Milky Way, then, is not static. It is alive with motion, stars orbiting, arms rippling, gas clouds collapsing, clusters drifting, companions merging. Every part of it tells a chapter in the great story of cosmic evolution. And though our solar system occupies a quiet suburb, we are embedded in a galaxy that is vibrant, restless, and endlessly fascinating. To understand the Milky Way is also to understand time on unimaginable scales. Our galaxy is about 13 billion years old, nearly as old as the universe itself. Some of the stars, still shining in its halo, were born when the cosmos was young, when heavy elements were scarce and only hydrogen and helium filled the void. These ancient suns are fossils of the early universe, their light carrying a memory of cosmic dawn. Not all stars live long, however. The galaxy is like a vast theater where lifespans vary dramatically. The most massive blue stars, blazing with furious energy, burn out in only a few million years. By contrast, tiny red dwarfs can persist for trillions of years, their glow steady and enduring. If the Milky Way were a library, each star would be a book written at a different pace, some brief and explosive, others slow and eternal. The solar system's location in the Orion Arm is not just a coincidence. It may be one of the reasons life was able to thrive on Earth. Here, far from the crowded galactic core, we are spared the constant bombardment of radiation and the chaos of frequent supernovae. Our neighborhood is relatively calm, a safe haven in which fragile molecules could assemble into life. Yet, evidence suggests Earth has still felt the galaxy's pulse. Past supernovae left traces of iron in our planet's crust, cosmic fingerprints reminding us that even from afar, the Milky Way can touch us. Beyond visible light, the galaxy reveals hidden faces. Infrared telescopes pierce the dusty shrouds of nebulae, unveiling newborn stars swaddled in cosmic clouds. Radio telescopes map the faint whispers of neutral hydrogen, tracing the skeleton of the Milky Way's spiral arms. X-ray observatories expose violent regions near black holes and exploding stars. To truly see our galaxy, we must use not one set of eyes, but the entire spectrum of light, each wavelength peeling back another layer of the story. The Milky Way is also a laboratory of extremes in chemistry. In giant molecular clouds, astronomers have discovered complex organic molecules, precursors to life. Alcohols, sugars, even amino acid-like structures drift in the cold darkness, assembled by cosmic processes long before planets formed. These discoveries suggest that the building blocks of biology are not unique to Earth. They're scattered generously across the galaxy, waiting to seed new worlds. Meanwhile, cosmic rays, high-energy particles accelerated by supernova shockwaves, race through interstellar space. They strike planets, alter atmospheres, and may even influence the course of evolution by mutating DNA. Though invisible and intangible, they are a constant reminder that the Milky Way is more than a passive backdrop. It is an active force shaping the fate of its inhabitants. Another extraordinary feature is the galactic rotation. Stars near the center orbit faster than those on the outskirts, yet the outer regions move more quickly than Newtonian physics predicts. This discrepancy is one of the strongest pieces of evidence for dark matter. Without this unseen mass, the spiral arms would fly apart. Instead, they hold together, proof of a hidden architecture that dominates the galaxy. The sheer scale of star systems within the Milky Way also inspires awe. Some stars dwarf the Sun so completely that if placed at the center of our solar system, their surface would extend beyond the orbit of Jupiter. Others are so faint and cool they barely glow, invisible without powerful telescopes. The galaxy contains every variety, from the tiniest embers of red dwarfs to the titanic furnaces of hypergiants. Each of these extremes contributes to the diversity of planetary systems. Around some stars, astronomers have found hot Jupiters, gas giants circling so close to their suns that their atmospheres boil away. Around others, frozen worlds orbit far out in the dark, silent and icy. And among them are rocky planets, scattered by the billions, some perhaps bearing oceans, mountains, and skies we can only imagine. The Milky Way is, in this sense, both an archive of the past and a promise of the future. It contains the seeds of countless stories, each written in the language of gravity, light, and time. The Milky Way is not a perfect disk, it is warped. Its outer edges bend and twist like the rim of a vast, uneven plate. Astronomers believe this warp is caused by gravitational interactions with satellite galaxies, like the Magellanic Clouds, or perhaps with a mysterious distribution of dark matter surrounding us. From afar, the galaxy would look less like a flat spiral and more like a majestic wave frozen in motion, its edges curling upward and downward across tens of thousands of light years. This warping reminds us that galaxies are not rigid structures, but flexible, living systems. The very stars we see above our heads are riding on a ripple of cosmic distortion, slowly shifting their positions over millions of years. Even the quiet suburbs of the Orion Arm are not immune to this grand, slow dance. Closer to home, the sun itself is not fixed in a flat plane. Our star weaves gently above and below the galactic disk, like a horse galloping on a carousel. This oscillation takes tens of millions of years, and during each passage, the solar system encounters regions of varying density. Clusters of stars, gas clouds, and even enhanced cosmic ray flux. Some scientists have wondered if Earth's cycles of mass extinctions might be tied to these periodic galactic motions, though the evidence remains tantalizing but uncertain. Surrounding the Milky Way is a vast halo of dark matter, invisible, yet outweighing all the stars combined. Embedded in this halo are faint, ancient stars and globular clusters, some so old they predate the spiral structure itself. These relics whisper the story of how the Milky Way assembled, not in one moment, but piece by piece, devouring smaller galaxies. The halo is like an attic filled with artifacts of forgotten times, where every star is a clue to the galaxy's origin. One striking example of this cannibalistic history is the Sagittarius dwarf galaxy, currently being torn apart by our own. Its stars are stretched into elongated streams wrapping around the Milky Way, a reminder that galaxies grow by merging, not unlike rivers that swallow tributaries. The halo is filled with such stellar streams, the ghostly trails of galactic meals from ages past. At the galactic center, meanwhile, life is anything but quiet. Surrounding the supermassive black hole is a region of extreme density, millions of stars crowded within a volume only a few light years across. Gas clouds spiral inward, heated to millions of degrees, emitting X-rays before vanishing past the event horizon. The central bulge glows with old, red stars, while bursts of star formation occasionally ignite in the surrounding disk. For astronomers, this core is both a mystery and a laboratory, where the interplay of gravity, radiation, and gas can be studied at its most intense. Beyond the visible disk, enormous structures extend far into intergalactic space. Gamma-ray telescopes have revealed colossal Fermi bubbles, two balloon-like lobes of energy stretching above and below the galactic plane. They may be relics of an ancient eruption from Sagittarius A-, or the cumulative effect of countless supernovae. These bubbles, invisible to human eyes, show that the Milky Way is capable of violence on a scale almost impossible to imagine. On smaller scales, stellar life cycles constantly reshape the galaxy. When massive stars explode, they enrich the surrounding medium with heavy elements. These elements drift, mix, and eventually condense into new stars and planets. It is a cosmic recycling program, ensuring that each generation builds upon the ashes of the last. Without this cycle, there would be no carbon for life, no silicon for planets, no iron for blood. The Milky Way is not just a collection of stars. It is a forge, eternally renewing itself. Even in the vast emptiness between stars, beauty persists. Dust grains scatter light, creating glowing reflection nebulae. Shock waves ripple outward, sculpting delicate filaments and arcs. Radio signals hum softly from hydrogen atoms aligned across the disk. To the naked eye, it may appear silent, but to our instruments, the galaxy is alive with soundless music, a symphony of radiation spanning the spectrum. One of the most compelling revelations of modern astronomy is the sheer diversity of planetary systems in the Milky Way. Where once we believed our solar system was unique, we now know there are billions, each with its own story. Some planets orbit so close to their suns that their surfaces glow with molten rock, while others wander far in the darkness, frozen giants adrift in perpetual night. There are even rogue planets, untethered to any star, drifting through the galactic void like lonely nomads. Among these worlds, astronomers search for Earth-like twins, planets in the habitable zones of their stars. Statistical studies suggest that in the Milky Way alone, there may be tens of billions of such planets. Imagine, nearly every patch of sky, if magnified, could hide entire families of worlds where oceans shimmer and atmospheres swirl. Though we have yet to glimpse life beyond Earth, the raw numbers tell us that the galaxy is not barren. It is fertile, seeded with endless possibilities. But not every environment in the Milky Way is gentle. Some regions are crowded with massive stars whose violent radiation strips atmospheres from nearby planets. Others lie near pulsars or black holes, where bursts of high-energy particles sterilize anything that might attempt to grow. The galaxy is a mosaic of both havens and hazards, with each neighborhood writing its own chapter in the cosmic narrative. Meanwhile, stellar remnants continue to intrigue. Neutron stars, though only about 20 kilometers wide, weigh more than the Sun. Their magnetic fields are trillions of times stronger than Earth's, bending space itself. In rare cases, these fields create magnetars, neutron stars whose eruptions can release more energy in a second than our Sun emits in 100,000 years. Such explosions ripple across the galaxy, detectable even from thousands of light years away. Another phenomenon unique to galaxies like ours is the presence of hypervelocity stars. These are suns flung from the galactic center by gravitational slingshots, racing through space at millions of kilometers per hour. Some of them will escape the Milky Way entirely, becoming eternal travelers between galaxies. To imagine an entire star cast adrift is to recognize the immense dynamism hidden behind the galaxy's calm facade. The Milky Way also carries scars of past interactions. The ripples in its stellar disk, the faint streams of orphaned stars, the warped outer edges, all speak of collisions and mergers. Astronomers now think our galaxy's spiral structure was shaped, at least in part, by encounters with smaller galaxies. These collisions may even have triggered waves of star formation, igniting new generations of suns and planets. Far from being isolated, the Milky Way is constantly sculpted by its neighbors. On the frontier of research lies the study of black hole populations. While the central supermassive black hole is well known, scattered throughout the galaxy may be millions of smaller black holes, remnants of collapsed stars. They drift invisibly, detectable only when they reveal themselves through X-rays or through the bending of starlight in gravitational lensing. The Milky Way is, in essence, riddled with these hidden wells, silent reminders of the deaths of countless stars. And yet, despite all these extremes, the galaxy maintains balance. Gravity binds its stars, rotation preserves its spiral arms, and cosmic recycling enriches its gas with heavy elements. It is a self-sustaining ecosystem, a cosmic rainforest where destruction and creation are intertwined. For every star that dies, another is born. For every world consumed, another takes shape. The Milky Way thrives because of this cycle, not in spite of it. To us, gazing from a small planet on the edge of one arm, the Milky Way may seem abstract, a concept more than a reality. But in truth, every breath we take, every atom in our bodies, every photon that warms our skin is a direct gift of this galaxy's ancient processes. We are not separate from it. We are a chapter in its story. The Milky Way is also home to some of the most catastrophic events in the cosmos, gamma-ray bursts. These are colossal explosions, often born from the collapse of massive stars or the merging of neutron stars. In a few seconds, they release more energy than the sun will emit over its entire lifetime. Thankfully, such bursts are rare and usually occur far from Earth, but their presence reminds us of the galaxy's violent undercurrents. Were one to happen close to us, it could strip atmospheres from planets and alter the course of life entirely. Yet in contrast to these destructive titans are the gentle cradles of star formation, stellar nurseries. The Eagle Nebula, with its famous pillars of creation, is one of many vast clouds sculpted by radiation and winds from newborn stars. Within these columns, gas condenses into dense knots, collapsing under gravity to ignite new suns. It is a process that has repeated for billions of years, ensuring the Milky Way is never static, but always replenishing itself with fresh light. Even the smallest components of the galaxy are fascinating. Interstellar dust grains, tiny particles of carbon, silicates, and ice drift between stars. Though individually minuscule, together they scatter starlight, painting the galaxy with hazy glows and dark lanes. These grains also serve as chemical factories, where molecules form on their surfaces, later becoming part of comets and planets. In this sense, dust is not just debris, but the seed of worlds to come. Cosmic migration also shapes our galaxy. Stars do not remain forever in the regions where they were born. Over time, gravitational interactions cause them to drift, spreading throughout the disk. This mixing ensures that the chemical elements forged in one part of the galaxy eventually enrich distant regions. Every atom of oxygen we breathe may once have belonged to a star born halfway across the Milky Way. The galaxy is threaded with invisible forces too. Magnetic fields, though weak compared to Earth's, extend across thousands of light years. They guide charged particles, shape the motion of gas, and influence star formation. To the human mind, magnetism feels abstract, but in galactic terms, it is a sculptor carving invisible patterns that leave visible marks in the way matter arranges itself. Even the central black hole, Sagittarius A-, is not always silent. Astronomical evidence suggests it has flared in the past, releasing powerful jets of energy. The giant Fermi bubbles that rise above and below the galactic plane may be the fossil record of such eruptions. These events reveal that the heart of the Milky Way can awaken, briefly transforming into a quasar-like engine that floods the galaxy with radiation. Meanwhile, at the edges of our spiral arms, stars gather into great associations known as open clusters. These groups, younger and looser than globular clusters, often contain only a few hundred stars. They are the siblings of stellar families, formed from the same cloud, shining together before slowly dispersing into the general population of the galaxy. The Pleiades, visible to the naked eye, is one such cluster, a delicate jewel box that gives us a glimpse of countless others scattered through the Milky Way. Astronomers also study the vertical structure of the galaxy: thin disk, thick disk, bulge, and halo. Each layer tells a different story. The thin disk is rich with young stars and gas, alive with ongoing star formation. The thick disk is older, populated by ancient suns that trace the galaxy's past. The bulge at the center contains tightly packed stars and mysteries still unsolved. Together, these structures form the skeleton and flesh of the Milky Way, a complex organism whose anatomy we are only beginning to understand. Finally, perhaps one of the most humbling facts: the Milky Way is but one of billions of galaxies in the observable universe. And yet, from our perspective, it is everything. Our cradle, our archive, our stage. To study it is to study ourselves, for we are inseparable from its history. The chemistry of stars offers another layer of the galaxy's story. Astronomers use the term metallicity to describe the abundance of elements heavier than hydrogen and helium in a star. Young stars, born from material enriched by countless supernovae, contain higher metallicities. Older stars, relics of the early galaxy, are poor in metals, their light carrying the signature of a more primitive cosmos. By mapping these chemical fingerprints, scientists can reconstruct the history of stellar generations, tracing how the Milky Way slowly became fertile ground for planets and life. Stars with higher metallicity are more likely to host planetary systems. This makes sense. Planets are built from the metals that stars forge. Our Sun, with a relatively high metallicity, was able to form a rich system of worlds, including Earth. In regions of the galaxy where metals are scarce, planets may be fewer, reminding us that the potential for habitable worlds is not evenly distributed but shaped by the galaxy's chemical evolution. The migration of giant planets also plays a decisive role. Observations suggest that many planetary systems are unstable in their youth. Gas giants can move inward or outward, reshaping or even destroying the smaller worlds in their path. In our own solar system, such migrations may have stirred up comets, delivering water and organics to Earth. Across the Milky Way, countless variations on this theme play out, creating a dazzling diversity of planetary architectures. Another subtle but profound feature of the Milky Way is its stellar streams, rivers of stars torn from smaller galaxies and clusters. These streams arc across the sky like faint scars, visible only through detailed surveys. They're the fossil trails of ancient mergers, reminders that the Milky Way is a work in progress, still assembling itself from the pieces of others. In the coming decades, missions like Gaia will map these streams with exquisite precision, giving us a cinematic record of our galaxy's cannibalistic past. Not all stars follow the serene spiral orbits we imagine. Some travel on wildly elliptical paths, plunging through the disk and soaring into the halo before returning again. These wanderers trace the gravitational complexity of the galaxy, each orbit a clue to the unseen distribution of matter. Their motions help astronomers weigh the Milky Way, refining our understanding of its invisible skeleton of dark matter. The galaxy also holds transient phenomena, fleeting, unpredictable, yet profound. Fast radio bursts, for example, are millisecond flashes of radio energy whose origins remain mysterious. Some may come from magnetars, others from still unknown processes. Their signals reach us from across the galaxy, whispering of extreme events that occur without warning. Each burst is a cosmic postcard, arriving suddenly, offering only a hint of its sender. The long-term future of the Milky Way is written in its motion. Our galaxy and the Andromeda Galaxy are on a collision course, set to merge in about 4 billion years. The event will not resemble a violent crash, but a slow intermingling, stars gliding past one another while gravitational tides reshape their orbits. Gas clouds will collide, igniting waves of star formation, while central black holes spiral together to form an even larger monster. In the aftermath, a new galaxy will emerge, a vast elliptical titan, carrying within it the blended legacy of both. But even this is not the end. Over trillions of years, star formation will slow as the supply of gas is exhausted. The Milky Way's once brilliant disk will fade, leaving behind a quieter population of long-lived red dwarfs and stellar remnants. The galaxy will grow dim, a shadow of its former self. Yet in those dim embers, life may still persist, clinging to worlds orbiting stars that shine faintly but steadily for ages beyond human imagination. The Milky Way, then, is not a static monument but a living timeline. Its past is written in the halos of ancient stars, its present in the glittering disk, and its future in the slow inevitability of cosmic evolution. To see it clearly is to see not just where we are, but where we came from and where we're going. One of the greatest challenges in studying the Milky Way is our vantage point. We are trapped inside it, gazing through veils of dust and clouds. Mapping the galaxy is like trying to understand a forest while standing among the trees. And yet, astronomers have devised ingenious methods to sketch its shape. By measuring the distances to stars through parallax, by tracing the radio glow of hydrogen, and by charting the positions of pulsars, we have slowly built a portrait of our spiral home. Missions like Gaia now refine this map, cataloging billions of stars and revealing the Milky Way in unprecedented detail. This mapping effort shows that the galaxy contains multiple spiral arms, each a region of denser stars and star-forming clouds. The Perseus arm, larger and brighter than our own Orion arm, lies further outward, while the Scutum Centaurus arm curves inward toward the center. Between these arms are gaps where stars are sparser, like valleys between mountain ridges. The arms themselves are not permanent structures, but dynamic waves of density, slowly shifting as the galaxy evolves. Star clusters provide additional windows into the galaxy's history. Open clusters, such as the Hyades, are loose associations of young stars, often only a few 100 million years old. Globular clusters, by contrast, are ancient, some nearly as old as the universe itself. Their tightly packed stars orbit far from the galactic plane, tracing the outer halo. By studying their ages and motions, astronomers piece together the sequence of events that built the Milky Way. Each cluster is a time capsule, preserving conditions from the era of its birth. The galactic bulge, a dense, peanut-shaped region at the core, offers its own mysteries. It is filled with older, reddish stars, but also shows evidence of star formation triggered by gas funneled inward along the spiral arms. The bulge is a crowded environment where stars are packed far more tightly than in our neighborhood. If Earth orbited there, the night sky would blaze with so many suns that true darkness would never fall. Surrounding the bulge is the central bar, a structure of stars and gas stretching across the inner disk. This bar acts like a gravitational engine, channeling material toward the center and influencing the spiral arms. Bars are common in galaxies, and the Milky Way's bar is a defining feature of its anatomy. Its slow rotation shapes the rhythm of the inner galaxy, a reminder that even at grand scales, order emerges from gravity's dance. Beyond visible matter, the Milky Way also contains a halo of hot gas extending for hundreds of thousands of light years. This halo is tenuous and invisible to human eyes, but it glows faintly in X-rays. It may contain more mass than all the stars combined, acting as a vast reservoir that regulates the galaxy's star formation. Like an atmosphere around a planet, the halo envelopes the Milky Way, connecting it to the larger intergalactic medium. The galaxy is not silent, either. Though sound cannot travel through the vacuum of space, oscillations ripple through the Milky Way's disk. Astronomers describe them as vertical waves, where stars and gas bounce above and below the plane. These oscillations may have been triggered by past collisions with dwarf galaxies, sending shudders through the disk like ripples in a pond. Even now, the galaxy vibrates with the echoes of ancient encounters. And while our own galaxy is massive, it belongs to a family. Together with Andromeda, the Triangulum Galaxy, and dozens of dwarfs, it forms the local group. This cluster of galaxies is bound by gravity, drifting together through space. Beyond it lies the Virgo supercluster, and beyond that, the cosmic web, a vast network of filaments stretching across the universe. The Milky Way is one node in this incomprehensibly large structure, its story intertwined with countless others. The Milky Way is a galaxy built on cycles. Stars are born, live, and die, and in doing so they continuously reshape the material fabric of the galaxy. The gas clouds of today were enriched by the ashes of yesterday's stars, and tomorrow's suns will inherit this legacy. It is a cosmic circle of birth and renewal, far grander than any cycle on Earth. The smallest stars, the red dwarfs, are the quiet workers of the galaxy. They burn their fuel so slowly that their lives stretch into trillions of years. None of them have yet died, since the universe itself is not old enough. Long after stars like our sun have faded, red dwarfs will remain, glowing faintly in the darkness. They are the future citizens of the galaxy, destined to outlive every other kind of star. Larger stars live faster, shorter, and more spectacular lives. A blue supergiant may shine millions of times brighter than the sun, yet it exhausts its fuel in just a few million years. Its end is dramatic. A supernova explosion, blasting heavy elements into space and leaving behind either a neutron star or a black hole. These explosions are not merely destructive. They are creative, seeding the galaxy with the raw ingredients of life. Even stars of medium size, like our sun, transform the galaxy. In their old age, they swell into red giants, shedding their outer layers into glowing shells of gas called planetary nebulae. These delicate structures, shaped like rings or butterflies, are temporary artworks in space, lasting only tens of thousands of years before dispersing. The cores of these stars shrink into white dwarfs, which will cool slowly for billions of years, fading like embers after a fire. The interstellar medium, the space between stars, is where the past and future meet. It contains the gas and dust expelled by dying stars, mixed with pristine material left over from the galaxy's formation. Supernova shock waves stir this medium, compressing clouds and triggering new waves of starbirth. In this way, the galaxy is self-sustaining. Every death plants the seeds of new creation. Chemical enrichment is one of the most profound outcomes of this cycle. The earliest stars contained almost nothing but hydrogen and helium. Today, stars and planets are laced with carbon, oxygen, silicon, iron, and more, the products of countless generations of stellar forges. Every planet, every ocean, every living cell owes its existence to this gradual accumulation of elements across billions of years. The Milky Way's diversity of stars also produces diversity in planetary systems. Around metal-rich stars, rocky planets like Earth are more common. Around older, metal-poor stars, giant planets of gas and ice dominate. This chemical gradient shapes the very possibility of life, making some regions of the galaxy more fertile than others. Astronomers sometimes speak of a galactic habitable zone, areas where the right balance of stability, elements, and distance from dangerous regions creates conditions friendlier to biology. Even exotic remnants leave their mark. Pulsars spinning neutron stars beam radio waves with precision so perfect they rival atomic clocks. Astronomers use them as cosmic lighthouses, triangulating positions and even testing Einstein's theories of gravity. Black holes, though invisible, sculpt their surroundings, consuming matter and releasing powerful jets that energize the interstellar medium. Each type of stellar corpse contributes to the galaxy's dynamism. To live in a Milky Way is to be part of this ongoing story. We are woven into the life cycles of stars, our atoms forged in their cores, our world assembled from their ashes. The galaxy is not just the backdrop of human history, it is the author of it. Measuring the true scale of the Milky Way has been one of humanity's greatest scientific quests. For centuries, we had no idea how vast our galaxy was, or even that we lived inside one. The night sky appeared as a dome of stars, scattered randomly above. It was only in the 18th and 19th centuries that astronomers began to suspect the stars formed a larger structure. Using careful counts of stars and, later, measurements of parallax and variable stars, they mapped the shape of the galaxy and placed the sun far from its center. What was once a mystery of myth became a chartable reality. A key breakthrough came with the discovery of Cepheid variable stars, suns that brighten and dim with clock-like regularity. The period of their pulsations correlates with their luminosity, making them cosmic yardsticks. By locating Cepheids across the sky, astronomers could measure the Milky Way's true extent. These same stars would later allow us to measure galaxies beyond our own, opening the door to the vast universe. Other methods soon followed. Radio astronomy revealed the spiral arms by mapping the 21-centimeter emission line of neutral hydrogen. This faint signal, invisible to the eye, allowed astronomers to trace the distribution of gas and sketch the skeleton of the galaxy. Pulsars and masers offered further anchors, their precise signals helping refine our understanding of distances. Today, spacecraft like Gaia measure the positions and motions of over 1 billion stars, producing the most detailed 3D map of the Milky Way ever made. Within this map, we see a galaxy of remarkable variety. Some regions are bustling nurseries filled with hot, bright stars that live short and dazzling lives. Others are quiet, populated by dim red dwarfs that may never exhaust their fuel. Stellar populations are categorized into groups. Population 1 stars are young and metal-rich, like our Sun, while Population 2 stars are older with fewer heavy elements. Hidden even deeper are hypothetical Population 3 stars, the first stars of the universe, long vanished but leaving chemical traces in their descendants. Occasionally, stars flare up in sudden outbursts. A nova occurs when a white dwarf siphons material from a companion star until the buildup ignites in a brilliant flash. Unlike supernovae, novae do not destroy the star, and the cycle can repeat again and again. These fireworks, once mistaken for new stars, are reminders that even the faintest remnants can spring back to life. The galaxy also acts as a cosmic lens. When a massive object passes between us and a distant star, its gravity bends the light, briefly magnifying it. This phenomenon, known as gravitational microlensing, allows astronomers to detect objects otherwise invisible: faint stars, brown dwarfs, even rogue planets. In this way, the Milky Way reveals itself not only through its light, but through the bending of space itself. Another rare event is the encounter between stars. Though the galaxy is crowded by human standards, the distances between stars are so immense that direct collisions are extraordinarily rare. But when they do occur, they create blue stragglers. Anomalously young-looking stars form from the merging of older ones. In dense clusters, these oddities stand out like rejuvenated actors on a stage, hinting at the occasional intimacy among stars. The more we probe the Milky Way, the clearer it becomes that our galaxy is both orderly and unpredictable. Its vast patterns, spiral arms, bulge, halo, obey the laws of gravity and motion, yet within those patterns unfold surprises. Novae, microlensing flashes, stellar mergers. The Milky Way is not a static diagram, but a living performance, a drama of light and matter that has played out for billions of years. Among the most intriguing stellar families in the Milky Way are associations and moving groups. Unlike dense clusters, these are loose gatherings of stars that share a common origin and drift through space together. Over millions of years, they gradually disperse, their members blending into the general galactic population. Yet their shared motions reveal their kinship, allowing astronomers to trace their ancestry back to the clouds where they were born. Runaway stars are another remarkable phenomenon. These are suns ejected from their birthplaces by gravitational slingshots or by the explosion of a companion in a binary system. Once freed, they streak through the galaxy at hundreds of kilometers per second. Some travel fast enough to leave the Milky Way entirely, destined to wander the intergalactic void. Imagine a night sky on a world orbiting such a star, where its sun races endlessly into the darkness, dragging its planets with it on a journey that will never return. Cosmic radiation also plays a subtle role in the Milky Way's ecology. High-energy particles, accelerated by supernovae and other energetic events, stream through interstellar space as cosmic rays. These invisible messengers constantly bombard planets and atmospheres. On Earth, they contribute to natural radioactivity and can even trigger mutations, influencing the path of evolution. Elsewhere in the galaxy, they may be catalysts for chemistry in planetary atmospheres or obstacles to fragile life. The Milky Way's disk is not uniform. It shows ripples, waves, and asymmetries. Astronomers suspect these disturbances were stirred by past collisions with dwarf galaxies. Like a pebble dropped into water, these encounters sent oscillations through the stellar sea, some of which we can still observe today. Our solar system itself rides one of these waves, a subtle undulation that reminds us that the galaxy is never entirely at rest. Brown dwarfs add another layer of mystery. Too small to ignite stable hydrogen fusion, yet too large to be considered planets. These failed stars drift quietly between the brighter suns. They glow faintly in infrared light, hidden from the naked eye. The Milky Way may contain billions of them, silent and unassuming, filling the spaces between stars with unseen companions. The galaxy is also threaded with giant molecular filaments, vast strands of gas and dust stretching for hundreds of light years. These filaments act as highways of star formation, where gravity fragments the clouds into clumps that eventually ignite as new stars. Seen in infrared, they resemble cosmic rivers flowing through the galactic plane, feeding the birth of generations of suns. Then there are chimneys and superbubbles, structures carved by the combined winds of massive stars and supernovae. These processes sweep out cavities in the interstellar medium, creating tunnels that channel gas and radiation into the halo. On cosmic scales, these bubbles act like the lungs of the galaxy, allowing it to breathe energy into its surroundings. Finally, the Milky Way's interaction with its environment reveals its interconnectedness. Streams of gas flow both in and out of the disk, some falling inward to fuel new stars, others blasted outward by stellar feedback. These flows connect the galaxy to the larger cosmic web, drawing in material from intergalactic space while contributing its own outflows. The Milky Way is not an isolated island, but part of a network of galaxies exchanging matter and energy. In every ripple, every runaway star, every invisible brown dwarf, the Milky Way demonstrates its complexity. It is a galaxy alive with motion and exchange, where nothing remains static and everything participates in the endless cycle of transformation. Among the galaxy's most spectacular laboratories are binary systems where stars interact in dramatic ways. When a compact object, a white dwarf, neutron star, or black hole, orbits close to a companion, it can siphon gas from the larger star. This stolen matter spirals inward, forming an accretion disk that glows with ferocious intensity. Such systems shine brightly in X-rays and can even outshine entire star clusters for brief periods. They are cosmic engines, powered by the relentless pull of gravity. In some cases, binary systems give rise to type Ia supernovae, events so luminous they can be seen across billions of light years. These explosions occur when a white dwarf accumulates too much material, exceeding a critical mass and detonating in a runaway fusion reaction. Type Ia supernovae are not only spectacular, they serve as standard candles for measuring cosmic distances, allowing us to gauge the expansion of the universe itself. Thus, the Milky Way's hidden binaries contribute directly to our understanding of the cosmos at large. Even more exotic are double neutron star systems. As these ultra-dense remnants spiral closer under the influence of gravity, they emit ripples in space-time known as gravitational waves. When they finally collide, the explosion is catastrophic, producing both a gamma-ray burst and heavy elements like gold and platinum. In fact, much of the precious metal on Earth was likely born in such mergers billions of years ago. Every ring on a finger, every piece of jewelry carries the memory of a stellar collision in the Milky Way's past. Black holes, too, may merge within the galaxy. Their unions, though invisible to telescopes, send gravitational waves sweeping across space. Instruments like LIGO and Virgo have already detected such signals, confirming predictions of Einstein's theory of relativity. Each detection is like hearing the heartbeat of the galaxy, vibrations carried across hundreds of millions of years. Not all endings are so violent. Some stars fade into obscurity, forming exotic remnants such as black dwarfs, the theoretical, cold descendants of white dwarfs that have radiated away all their heat. None exist yet, since the universe is not old enough, but trillions of years from now, the Milky Way will be filled with these dark, silent cinders. They represent the ultimate fate of many stars. Not explosion, but quiet extinction. Even within stellar deaths, variety abounds. Some stars shed their outer layers gently, forming planetary nebulae with intricate shapes sculpted by magnetic fields or unseen companions. Others collapse asymmetrically, producing kick velocities that send neutron stars hurtling through the galaxy like cosmic bullets. Each outcome adds texture to the Milky Way's evolving story, ensuring that no two endings are ever quite the same. The galaxy also contains rare oddities. Thorn, Zitko objects, hypothetical hybrids of a red supergiant and a neutron star, with a compact core burrows into the giant's envelope. Though none have been definitively confirmed, the possibility of such stellar chimeras shows how strange the Milky Way can be. Nature's creativity often surpasses our imagination, and the galaxy is her greatest canvas. Through gravitational waves, X-ray flares, and shimmering nebulae, the Milky Way tells us that endings are not final. Each death enriches the galaxy. Each merger reshapes its structure, and each invisible wave links us to cosmic dramas unfolding far beyond human reach. The galaxy is not merely a collection of stars, but a theater of transformations, some quiet, some cataclysmic, all essential to the cycle of creation. The grand architecture of the Milky Way is shaped by subtle but powerful forces. Spiral arms, for instance, are not permanent arrangements of stars, but density waves that ripple through the disk. They act like cosmic traffic jams. As stars and gas enter the wave, they slow and pile up, becoming brighter and denser. Once through, they continue on their way, while the wave itself persists. These arms are not rigid structures, but patterns in motion, endlessly regenerating as the galaxy rotates. The central bar also plays a crucial role in sculpting the galaxy. Stretching across thousands of light years, this elongated concentration of stars and gas influences the orbits of material in the inner disk. It acts like a galactic engine, funneling gas toward the core where it fuels bursts of star formation and activity around the central black hole. Over time, this bar may grow longer or dissolve entirely, reshaping the Milky Way's overall appearance. Stellar migration is another quiet but transformative process. Stars rarely remain where they were born. Gravitational interactions, resonances with spiral arms, and encounters with molecular clouds can gradually shift their orbits inward or outward. As a result, the Sun itself may not have formed in its current location. Over billions of years, stars mix throughout the disk, blending populations and ensuring that the chemical wealth created in one region spreads across the galaxy. These migrations have profound consequences for planetary systems. A star born in a hazardous environment near the galactic center might eventually drift into calmer suburbs, carrying its planets and any potential life with it. Conversely, stars from safer regions might wander into more perilous neighborhoods, exposing their worlds to radiation or disruptive encounters. The galaxy is not static. It constantly reshuffles its inhabitants, like a deck of cards in eternal motion. Beyond the disk, tidal interactions leave imprints on the Milky Way structure. Dwarf galaxies caught in our gravity, are slowly torn apart, their stars stretched into streams that wrap around the halo. These streams act as fossils, preserving the memory of ancient mergers. By studying their paths, astronomers can reconstruct the Milky Way's growth, much like archaeologists tracing layers of history in stone. Resonances within the galaxy create further patterns. At certain orbital speeds, stars and gas are trapped in synchronized motions, reinforcing spiral arms or carving gaps in their distribution. These resonances act like invisible harmonics, orchestrating the flow of matter on scales too vast for the human mind to fully imagine. The result is a galaxy that is both chaotic and ordered, governed by the interplay of randomness and rhythm. At the very edge of the Milky Way, faint stellar populations extend far beyond the main disk. Some of these stars may have been captured from intergalactic space, others thrown outward during gravitational encounters. Their presence shows that the galaxy's boundaries are not sharp but blurred, fading gradually into the cosmic web. The Milky Way's influence stretches much farther than its bright disk suggests, linking us to the larger environment of the local group. In this ever-changing framework, stars are not merely passengers but participants. Their births and deaths feed back into the structure, fueling density waves, stirring turbulence, and driving flows of gas. The Milky Way is not a static spiral painted once and forever. It is a living organism, reshaping itself with every passing million years. The Milky Way's visible disk is only the beginning. Beyond the shining spiral arms lies a vast, diffuse stellar halo, stretching hundreds of thousands of light years in all directions. This halo is sparsely populated, containing ancient stars and globular clusters, as well as faint tidal streams from galaxies long ago consumed. Though ghostly and faint, the halo is essential. It preserves the record of the Milky Way's formation, a cosmic archive of every encounter and merger. Orbiting within this halo are dozens of dwarf galaxies, most of them barely luminous. The Sagittarius dwarf and the Magellanic Clouds are the most prominent, but astronomers continue to discover ultra-faint dwarfs, collections of only a few thousand stars, bound together in fragile clusters. These galaxies are laboratories of dark matter, since their visible mass is too small to explain their cohesion. In them, we see dark matter's grip most clearly, holding together what light alone could not. Beyond even the halo lies the circumgalactic medium, CGM, an immense reservoir of hot, ionized gas that envelopes the galaxy like an unseen cocoon. This medium stretches for millions of light years and may contain more matter than all the stars in the disk combined. It is both a source and a sink, feeding the galaxy with fresh gas for star formation while also absorbing the outflows from supernovae and galactic winds. The CGM is the Milky Way's interface with the larger cosmic web, connecting us to intergalactic space. The discovery of stellar streams in the halo has revolutionized our view of the galaxy. These streams are the torn remains of dwarf galaxies and clusters, stretched into filaments by tidal forces. They crisscross the halo like trails of cosmic smoke, each marking the path of a past collision. By charting their motions, astronomers can not only reconstruct the Milky Way's history, but also map the invisible distribution of dark matter. The halo is a testing ground for the galaxy's unseen architecture. The Magellanic Clouds, the large and small Magellanic Clouds, are unique among the Milky Way's companions. Visible from the southern hemisphere, they are irregular galaxies, rich in gas and star formation. A stream of gas, known as the Magellanic Stream, stretches tens of thousands of light years behind them, feeding material into the Milky Way. This cosmic umbilical cord shows that galaxies are not self-contained, but exchange matter across intergalactic space. In recent years, astronomers have also identified orphan streams with no visible progenitors. These mysterious trails suggest that entire dwarf galaxies may have been completely shredded and absorbed, leaving behind only their scattered stars. The halo, then, is not just a graveyard of past galaxies, but an active record of the Milky Way's ongoing growth. Even high above the galactic plane, lone stars wander. Some belong to the stellar halo. Others were ejected from the disk through gravitational interactions. They drift silently through the dark, far from the bustling spiral arms, serving as reminders that the Milky Way is larger and more diffuse than our eyes can ever perceive. The halo and CGM remind us that galaxies are not simple disks of stars. They are layered, extended ecosystems, exchanging matter with their surroundings and carrying the fingerprints of billions of years of cosmic evolution. The Milky Way, though it feels intimate as our home, is in truth a sprawling giant whose reach extends far into intergalactic space. The Milky Way does not exist in solitude. It belongs to a small but significant family of galaxies known as the Local Group. This cluster contains more than 50 members, from giants like Andromeda and Triangulum to tiny dwarfs with only a few thousand stars. Gravity binds them together, pulling them through space as a single, loosely knit community. Within this group, the Milky Way is one of the dominant players, its immense mass shaping the orbits of its smaller companions. The most dramatic relationship in this group is between the Milky Way and Andromeda. Both galaxies are rushing toward each other at nearly 110 kilometers per second. Although separated by 2.5 million light-years today, they are destined to merge in about 4 billion years. To human scales, this sounds apocalyptic, but on galactic scales, it is a graceful dance. The stars within each galaxy are so far apart that few will collide directly. Instead, gravity will stretch and distort their spiral arms, flinging streams of stars into intergalactic space. Eventually, the two will settle into a single, massive elliptical galaxy, a new home forged from two ancient ones. Triangulum, the third largest galaxy of the Local Group, may also play a role in this cosmic ballet. It could be captured during the merger, joining the collision and contributing to the final remnant. Smaller dwarfs, like the Magellanic Clouds, are already being pulled and reshaped by the Milky Way's gravity. This constant interchange of matter shows that galactic evolution is communal, not isolated. Galaxies grow by interacting, colliding, and merging. Beyond the Local Group lies an even larger structure, the Virgo supercluster. The Milky Way and its neighbors are but a small branch of this sprawling complex, which itself is only a filament in the greater cosmic web. On the largest scales, galaxies trace out enormous strands of matter, leaving behind vast voids of emptiness. The Milky Way, then, is not just a spiral of stars, but a node in this universal network, linked by gravity to structures far beyond our comprehension. The Milky Way's motion through this web is astonishing. Our galaxy is being drawn toward a gravitational anomaly known as the Great Attractor, a region of immense mass hidden behind the plane of the Milky Way itself. Beyond that lies the Laniakea supercluster, a gravitational basin containing hundreds of thousands of galaxies. Within this vast river of matter, the Milky Way drifts like a leaf on a current, part of a flow that spans hundreds of millions of light years. Despite this grand connectivity, our perspective is local. For us, the Milky Way defines reality. Yet its links to Andromeda, to the Local Group, and to the larger cosmic web remind us that no galaxy is an island. Every star we see at night is part of a chain of connections stretching outward into infinity. This interconnectedness also shapes the future of astronomy. As instruments improve, we are beginning to detect the faint bridges of gas and dark matter that tie galaxies together. Already, telescopes reveal streams of hydrogen flowing between the Milky Way and its companions, threads of cosmic fabric weaving our galaxy into its environment. In time, we may uncover even deeper structures, proving that the Milky Way is not a self-contained system, but a participant in a cosmic community on scales that dwarf imagination. Studying the Milky Way requires a blend of ingenuity and technology. Because we cannot step outside to look at it directly, astronomers rely on instruments that capture light across the entire electromagnetic spectrum. Each wavelength acts like a different sense, revealing details invisible to ordinary eyes. Invisible light. The galaxy appears as a glowing band scattered with dark patches. Those patches are not empty space, but dense clouds of dust, hiding stars behind them. Infrared telescopes, however, pierce through this veil, unveiling clusters of newborn stars still swaddled in their birth clouds. The Spitzer Space Telescope and now the James Webb Space Telescope have revealed entire nurseries otherwise cloaked in shadow, offering intimate views of stellar origins. Radio astronomy adds yet another layer. Hydrogen, the most abundant element in the galaxy, emits a faint signal at 21 centimeters. By mapping this emission, astronomers trace the Milky Way's spiral arms and measure their rotation. Enormous radio arrays like the Very Large Array in New Mexico or the upcoming Square Kilometer Array provide the precision needed to uncover faint structures stretching across the disk and halo. X-ray and gamma-ray observatories, meanwhile, expose the galaxy's violent side. They detect the searing glow of matter spiraling into black holes, the shock waves of supernovae, and the vast Fermi bubbles towering above and below the galactic plane. To study the Milky Way in these wavelengths is to glimpse its raw power, the invisible energy that shapes its evolution. Surveys from space missions have revolutionized our view. The Gaia spacecraft, launched by the European Space Agency, is charting the positions and motions of more than 1 billion stars with exquisite accuracy. It has already uncovered streams from ancient mergers, ripples in the galactic disk, and new details about the sun's orbit. Gaia is not merely mapping stars. It is reconstructing the Milky Way's biography, one data point at a time. Other missions add further detail. The Kepler Space Telescope revealed the ubiquity of planets, showing that exoplanets are not rare, but abundant. The Hubble Space Telescope, though best known for its images of distant galaxies, has also provided critical data on globular clusters and stellar populations within our own. Each instrument contributes a brushstroke to the vast mural of the Milky Way. The future promises even deeper insights. The Vera-C Rubin Observatory, with its wide-field surveys, will monitor the sky night after night, capturing transient events, novae, variable stars, microlensing flashes across the galactic plane. The Nancy Grace Roman Space Telescope will extend our ability to study exoplanets and dark matter, probing both the small-scale details and the grand structure of our galaxy. Even gravitational wave observatories are part of this future. As space-based detectors like LISA come online, they will listen for the murmurs of merging black holes and neutron stars within the Milky Way. For the first time, we will not only see the galaxy with light, but hear it through the vibrations of space-time itself. Together, these observatories transform the Milky Way from a hazy band in the night sky into a richly detailed, multidimensional object. Each new discovery peels back another layer, proving that even our own home galaxy remains as mysterious as the distant realms we yearn to explore. The Sun, though just one star among hundreds of billions, has a unique place in the Milky Way. It orbits the galactic center at a speed of about 828,000 kilometers per hour, taking roughly 225 to 250 million years to complete one revolution. This means that since its formation 4.6 billion years ago, the Sun has circled the galaxy only about 20 times. Each galactic year is unimaginably long compared to the scale of human history, but for the galaxy, it is merely the tick of a cosmic clock. As a solar system makes its way around the galaxy, it does not follow a perfectly flat path. Instead, it weaves gently above and below the galactic plane in a slow oscillation that takes tens of millions of years. During these cycles, Earth is exposed to different cosmic environments, sometimes drifting through calmer regions, sometimes passing through denser clouds of gas or regions enriched with cosmic rays. Some scientists have speculated that such journeys may have influenced mass extinctions or climate shifts on Earth, though the evidence remains debated. Our location in the Orion Arm, between the larger Sagittarius and Perseus arms, provides a relatively quiet neighborhood. The galactic center, with its crowded stars and powerful radiation, would be far more hostile to life. In this sense, our placement may not be accidental, but a condition that allowed Earth to develop biology. Astronomers even speak of a galactic habitable zone, a region not too close to the violent center and not too far into the metal-poor outskirts, where the chances for life-bearing planets are greatest. Our solar system lies within this zone, a fortunate circumstance in the vast sweep of the galaxy. Evidence of the Milky Way's influence on Earth is written into the geological record. Traces of iron-60, a radioactive isotope, have been found in ocean sediments, likely deposited by nearby supernovae in the past few million years. Such explosions may have altered Earth's atmosphere and even shaped the path of evolution. Our planet, though seemingly isolated, is deeply connected to events playing out light years away. The Sun itself is not alone. It belongs to a moving group, a collection of stars with similar motions, likely born from the same stellar nursery billions of years ago. Over time, these siblings have drifted apart, scattered across the galaxy. Astronomers continue to search for the Sun's lost brothers and sisters, stars that share its age and chemical fingerprint. To find them would be to uncover our stellar family tree, tracing our origins to a long-vanished cloud of gas and dust. Looking ahead, the solar system's journey will carry it into new regions of the Milky Way. Over millions of years, gravitational interactions may subtly alter its orbit, shifting its course inward or outward. Eventually, as the galaxy merges with Andromeda, the Sun will be flung into a new configuration, perhaps orbiting a completely different galactic center. By then, Earth may no longer exist as it does today, but the solar system will still be a passenger in the galaxy's endless voyage. In this way, our story is inseparable from the Milky Way's. The rhythms of our planet, from the elements in its crust to the cosmic rays that touch its atmosphere, are woven into the galaxy's larger dance. To understand the Milky Way is not only to study distant stars, but to see the hidden threads that connect our world to the grand design of the cosmos. Not all stars in the Milky Way are alike, and their differences tell the story of how the galaxy evolved. Astronomers categorize stars into populations based on their chemical composition and age. Population 1 stars, like the Sun, are relatively young and rich in heavy elements. These stars are concentrated in the thin disk, particularly in the spiral arms, where new generations are continuously born. They're the heirs of billions of years of stellar recycling, carrying in their atmospheres the fingerprints of countless supernovae. Population 2 stars are older, poorer in heavy elements, and typically found in the thick disk, the bulge, and the halo. Many of them formed in the galaxy's earliest epochs, when only the first supernovae had enriched the interstellar medium. These ancient suns are fossils of the early Milky Way, their chemical simplicity reflecting a time when the periodic table had not yet been fully written in the hearts of stars. The elusive population 3 stars remain hypothetical. These would have been the very first stars of the universe, composed almost entirely of hydrogen and helium. They were massive, short-lived, and long gone, but their legacy endures in the chemical makeup of later generations. By studying metal-poor stars in the halo, astronomers hope to glimpse the fingerprints of those primordial giants, whose deaths seeded the galaxy with the first heavy elements. The distribution of metals, astronomers' shorthand for all elements heavier than helium, varies across the Milky Way. In the inner regions, closer to the galactic center, stars tend to be more metal-rich, a sign of vigorous star formation and recycling over billions of years. In the outer halo, stars are metal-poor, some with only trace amounts of heavier elements. This gradient reflects the galaxy's growth. Its heart evolved quickly, while its outskirts remained more primitive. Globular clusters add another dimension to this picture. These dense spheres of stars orbit far above and below the galactic plane, and many are among the oldest structures in the galaxy. Their stars are almost uniformly metal-poor, evidence of their ancient origins. Yet some clusters show multiple populations, suggesting that even in the early galaxy, processes of enrichment and renewal were already at work. Each cluster is a frozen chapter from the dawn of the Milky Way. By analyzing the spectra of stars, astronomers can read their chemical compositions like barcodes. Ratios of elements, such as magnesium, iron, and carbon reveal the history of supernova contributions. Some stars carry signatures of enrichment by massive stars, others by smaller, long-lived ones. Together, they form a chemical map of the galaxy's past, a record etched into the atmospheres of billions of suns. This chemical diversity also shapes planetary formation. Stars rich in metals are more likely to host rocky planets, while stars poor in metals may favor gas giants or none at all. Thus, the likelihood of habitable worlds depends on a galaxy's chemical evolution. Our very existence on Earth is tied to the enrichment history of the Milky Way. Without generations of earlier stars building up carbon, oxygen, and iron, there would be no ground beneath our feet, no water in our oceans, no oxygen in our lungs. Through these populations and chemical fingerprints, the Milky Way reveals its biography, a tale of rapid youth, steady growth, and ongoing renewal. To study the stars is to study the history of the galaxy itself. For every atom of light they shine carries a memory of when and where they were born. The Milky Way is a galaxy of contrasts, where the density of stars changes dramatically depending on where you are. Near the galactic center, stars are packed so tightly that distances between them can be measured in mere fractions of a light year. If Earth were located there, the night sky would blaze with thousands of suns, their combined glow erasing the darkness completely. In this crowded heart, stellar orbits whip around the central black hole, and gravitational interactions constantly reshape their paths. It is a place of intensity and chaos, where stars live fast and die young. By contrast, the outer halo is almost empty. Here, stars are separated by tens or even hundreds of light years, drifting quietly in isolation. These halo stars are ancient, survivors from the galaxy's earliest days or from devoured dwarfs. Life in the halo would be lonely. A planet orbiting one of these suns would see only the faint smear of the Milky Way across its sky, with few nearby stars for company. In between lies the disk where the sun resides. Our stellar neighborhood is moderate. Stars are on average a few light years apart, offering a balance between density and emptiness. This spacing provides stability for planetary systems. Close encounters that could disrupt orbits are rare, but the sky is still full of thousands of stars visible to telescopes. It is in regions like this that life may have the best chance to persist, protected from the extremes of the core, yet enriched by billions of years of stellar evolution. Star clusters represent microcosms of density. Open clusters, like the Pleiades, contain dozens to hundreds of stars bound loosely together. In these nurseries, stars form in groups, like siblings, before slowly dispersing into the galaxy. Globular clusters, however, are far more extreme. Hundreds of thousands of stars compressed into a sphere only a few dozen light years across. Inside such a cluster, night skies would be crowded with brilliant lights, and the chance of close encounters between stars would be high. High-density environments can shape the destinies of planets. In the core or in dense clusters, the gravitational pull of passing stars could strip planets from their orbits, creating free-floating worlds. Radiation from nearby supernovae could sterilize planets or blow away their atmospheres. In these crowded regions, planetary systems live precarious lives. By contrast, in the galactic outskirts, planets may orbit undisturbed for billions of years, though at the cost of fewer heavy elements to build Earth-like worlds. The Milky Way's density extremes also influence star formation. In spiral arms, where gas and dust are denser, new stars ignite in great numbers. Between the arms, star formation slows, and the regions are quieter. In the halo, almost no new stars are born at all. Thus, the galaxy is not uniform but patchy, with hotbeds of creation and deserts of inactivity coexisting side by side. This variation in density paints the Milky Way as a mosaic of environments, each with its own rules. From the fiery core to the lonely halo, stars and planets experience vastly different fates. And yet, all are part of the same galactic organism, connected by gravity and history, contributing to the evolving story of our cosmic home. The Milky Way is not only a cradle of stars and planets, it is also a source of danger. Across its vast expanse, violent events release energy capable of reshaping entire regions. Supernova explosions, for example, send shockwaves racing through interstellar space. These waves compress nearby gas clouds, sometimes triggering new rounds of star formation, but they also flood their surroundings with radiation and high-energy particles. A planet too close to such a blast could lose its atmosphere or see its biosphere sterilized in moments. Even more extreme are hypernovae, explosions of the most massive stars, which can be 10 times more energetic than ordinary supernovae. These events are often linked with long-duration gamma-ray bursts, narrow beams of radiation that, if aimed directly at a planet, could devastate its atmosphere. Luckily, the odds of Earth being in the crosshairs of such a burst are slim, but the potential illustrates how the galaxy can shape the destiny of life on its worlds. Beyond these cataclysms, the galaxy constantly bathes its planets in cosmic rays. These high-energy particles, accelerated by supernova remnants and other violent processes, rain down across interstellar space. They penetrate atmospheres, trigger chemical reactions, and may even influence cloud formation on planets. On Earth, they are both a hazard and a creative force, occasionally mutating DNA in ways that could spark evolutionary leaps. In other corners of the Milky Way, cosmic rays may play similar roles, both threatening and fostering life. The galaxy also hosts unstable stars that unleash powerful flares. Magnetically active red dwarfs, for instance, can erupt with blasts far stronger than anything our sun produces. For planets orbiting close to such stars, these flares can strip atmospheres or bombard surfaces with radiation. Given that red dwarfs are the most common stars in the Milky Way, entire swaths of planetary systems may live under skies that flare unpredictably, making habitability a fragile balance. At the galactic center, additional hazards await. The supermassive black hole Sagittarius A is usually quiet, but evidence suggests it has flared in the past, releasing jets of energy that carved enormous structures into the halo. If such an eruption were to occur again on a large scale, its radiation could ripple outward for thousands of light years, altering conditions in wide swaths of the galaxy. Even dormant giants can awaken. Collisions between stars, though rare, are another hazard. In dense clusters or near the core, stars can pass close enough to disturb each other's planetary systems. Some encounters may eject planets into interstellar space, while others may send comets hurtling toward inner worlds. These gravitational brushes are invisible threats, unfolding over timescales too vast for human awareness, yet they constantly reshape the architecture of stellar neighborhoods. Despite these dangers, the galaxy also provides stability. The sun's placement in a relatively calm arm, away from the core and dense clusters, shields Earth from many of the most extreme hazards. This balance between danger and safety may be one reason life had the chance to flourish here. The Milky Way, in this sense, is both a nurturing parent and a stern teacher, capable of granting life and ending it with equal ease. Every hazard is also part of the cycle. Supernovae seed the galaxy with elements, flares stir chemistry in young atmospheres, and even cosmic rays may act as sparks for biological novelty. The Milky Way's dangers are not merely destructive. They are woven into the fabric of creation itself. The Milky Way is not a static system. It pulses with rhythms that play out over millions and billions of years. One of the most fundamental cycles is the pattern of star formation. Gas clouds collapse into clusters of stars, which in turn produce winds and explosions that stir the surrounding medium. These violent outbursts disperse the remaining gas, halting further starbirth, but only temporarily. Over time, the gas cools and gathers again, beginning a new cycle. The galaxy breathes in this way, inhaling and exhaling stars with cosmic regularity. The spiral arms are central to this rhythm. As density waves sweep through the disk, they compress gas and dust, sparking bursts of star formation. The bright blue stars we see lining the arms are evidence of this process, short-lived giants that mark the locations of recent stellar nurseries. Between the arms, the pace slows and the population shifts toward older, redder stars. This alternation creates a galactic heartbeat, with arms and interarm regions beating out the rhythm of creation and decay. The sun's journey around the galaxy may also follow hidden cycles. Some scientists suggest that as the solar system passes through spiral arms, Earth experiences higher exposure to supernovae and cosmic rays, potentially influencing climate or extinction events. Though evidence remains uncertain, the idea underscores the connection between our planet's history and the larger movements of the galaxy. Earth's story is not written in isolation, but intertwined with these immense galactic patterns. On longer scales, the Milky Way itself oscillates. Its disk ripples above and below an imaginary midplane, likely stirred by past encounters with dwarf galaxies. These vertical waves propagate across tens of thousands of light years, slowly dampening, but leaving behind traces in the motions of stars. Astronomers, using Gaia data, have begun to detect these patterns. The galaxy itself ringing like a cosmic bell struck long ago. Gas flows also follow cycles. Material falls inward from the circumgalactic medium, fueling new star formation, while stellar winds and supernovae drive gas outward into the halo. This galactic fountain recycles matter across scales of hundreds of thousands of light years, ensuring that the Milky Way remains dynamic. Without this constant exchange, the disk would exhaust its supply of gas in just a few billion years. Instead, the galaxy sustains itself, balancing inflows and outflows like a living ecosystem. Another rhythm is encoded in the orbits of stars. While most follow circular paths around the center, subtle resonances trap groups of stars into shared motions. These resonances can create gaps in the distribution of stars, or bunch them into streams that orbit in synchrony. They are the hidden harmonies of the galaxy, evidence that even chaos is guided by order on grand scales. Even the dark matter halo may contribute to these rhythms. As the invisible mass interacts gravitationally with the visible disk, it can stir waves, alter star orbits, and influence the rate of star formation. Though unseen, its presence is part of the galaxy's long-term pulse, shaping its evolution from behind the curtain. In these cycles of star birth, spiral arm passage, gas recycling, and gravitational resonance, the Milky Way reveals itself as more than a collection of objects. It is a symphony, its instruments, stars, and gas. Its measures millions of years long. To perceive it is to glimpse the music of the cosmos, playing endlessly in the background of our existence. Among the Milky Way's countless stars lie objects so strange they defy ordinary categories. Ultra-compact binaries, for example, are pairs of white dwarfs, neutron stars, or black holes orbiting each other in impossibly tight embraces. Some whirl around each other in mere minutes, their orbits shrinking as they radiate gravitational waves. These pairs are invisible to the naked eye, yet they're some of the most exotic laboratories of physics in the galaxy, where matter and space-time interact at the limits of known science. Other extremes include magnetars, neutron stars with magnetic fields 1,000 times stronger than typical pulsars. Their surfaces are tortured landscapes where atoms themselves are distorted by magnetism. Occasionally, magnetars unleash bursts of energy so powerful they can be detected across the entire galaxy. In a single second, they can release as much energy as the sun does in 100,000 years. These rare giants remind us that even dead stars can wield unimaginable power. There are also mysterious stars that blur the line between categories. Some hypergiants balloon to sizes so vast they would engulf the orbits of Jupiter or Saturn if placed at the center of our solar system. Others shrink into ultra-faint dwarfs, glowing so dimly that even with powerful telescopes they are hard to detect. The diversity of stellar extremes within the Milky Way is staggering, a cosmic catalog ranging from fiery titans to embers on the brink of invisibility. Beyond stars, strange objects populate the galaxy. Brown dwarfs, often called failed stars, bridge the gap between planets and suns. Too small to ignite stable fusion, they glow faintly in infrared, their atmospheres whipped by exotic weather. Some may host moons or planetary companions of their own, forming miniature systems adrift between the brighter lights of true stars. The Milky Way is also home to enigmatic fast radio bursts, brief flashes of radio waves lasting only milliseconds. Their sources are still debated. Some may arise from magnetars, others from interactions we cannot yet explain. Though they release their energy in the blink of an eye, they shine brighter than entire galaxies for that instant. Detecting them is like catching lightning across cosmic distances, and each burst is a clue to phenomena we are only beginning to understand. At the smallest scales, the galaxy may even contain primordial black holes, hypothetical remnants from the earliest moments of the universe. If they exist, they could range from asteroid size to planetary mass, invisible save for their gravitational influence. While still unproven, the idea suggests that some of the Milky Way's unseen mass might be made of these ancient relics, lurking silently between the stars. Exotic binaries also create spectacular fireworks. When two white dwarfs spiral together, they may merge into a single, more massive star or explode in a thermonuclear outburst. Such events are rare, but they enrich the galaxy with heavy elements and remind us that even quiet stellar remnants can suddenly erupt into brilliance. These extremes, magnetars, hypergiants, failed stars, and fleeting bursts, are not oddities but integral parts of the Milky Way's ecosystem. They stretch the boundaries of what is possible, filling the galaxy with phenomena that challenge both our instruments and our imagination. To explore them is to test the very edges of physics, where the familiar laws of nature bend under pressure and reveal new mysteries. The Milky Way was not born as the elegant spiral we see today. In its earliest form, more than 13 billion years ago, it was a chaotic collection of smaller proto-galaxies. These primitive structures collided and merged, their stars and gas gradually coalescing into a single, growing system. The ancient halo stars and globular clusters we observe today are relics of this violent youth. Fossils from a time when the galaxy was still stitching itself together from cosmic fragments. As billions of years passed, the Milky Way's disk began to take shape. Gas settled into a rotating plane, where density waves carved out the first spiral structures. Star formation ignited across the disk, producing generations of suns and enriching the interstellar medium with heavier elements. This process gave rise to the thick disk and later, the thinner, more orderly disk where we now reside. Each stage of assembly left its imprint in the motions and chemistry of the stars, a record that astronomers are only now learning to decipher. The galaxy's growth was fueled by mergers. Smaller galaxies, drawn in by gravity, were torn apart, their stars stretched into streams and absorbed. Even today, this process continues. The Sagittarius dwarf galaxy, for example, is currently being shredded, its remnants wrapping around the Milky Way in looping arcs. The Magellanic Clouds, too, are destined to eventually merge, their gas already feeding star formation in our disk. The Milky Way is not a finished product, but a work in progress, constantly reshaped by cosmic interactions. Looking to the future, the most dramatic transformation will come with the merger of Andromeda. In about 4 billion years, the two giants will collide in a slow-motion dance lasting billions of years. Spiral arms will unravel, tidal streams will fling stars into intergalactic space, and central black holes will spiral together, releasing gravitational waves across the cosmos. In the end, the Milky Way and Andromeda will settle into a massive elliptical galaxy, sometimes nicknamed Milkomeda. Though individual stars will rarely collide, planetary orbits may be disrupted, altering the fates of countless worlds. On even longer timescales, star formation will gradually decline. As gas supplies are consumed or expelled, fewer new stars will be born. The bright blue giants will vanish first, leaving behind long-lived red dwarfs and stellar remnants. Trillions of years from now, the galaxy will fade into a quieter, dimmer state, its spiral arms dissolved, its core dominated by black holes and white dwarfs. The Milky Way story will not end in fire, but in a slow descent into darkness. Yet even in this far future, echoes of vitality remain. Red dwarfs will shine steadily for trillions of years, outlasting every other star. Planets around them may continue to host life long after Earth is gone. Black holes, though silent, will merge and release gravitational waves. The galaxy, though dimmed, will remain a participant in cosmic evolution until the universe itself changes beyond recognition. The Milky Way, then, is both a fleeting structure and an enduring presence. Its spiral arms, its current brilliance, its ongoing starbirth. These are temporary phases in a story billions of years long. To glimpse its past is to see chaos transformed into order. To imagine its future is to witness order dissolving back into silence. The galaxy is not eternal, but its legacy will stretch across time scales far beyond human comprehension. The visible stars and gas of the Milky Way are only part of the story. Surrounding the galaxy is an enormous halo of dark matter, invisible, undetectable by ordinary light, yet outweighing all the luminous material combined. Without this halo, the Milky Way could not hold itself together. The stars in the outer disk move too quickly to be bound by visible matter alone. Dark matter's gravity provides the glue, ensuring the spiral arms do not unravel into space. The shape of this dark halo is still uncertain. Some models suggest it is roughly spherical, others that it is elongated or triaxial. By studying the motions of satellite galaxies and stellar streams, astronomers attempt to map this hidden scaffold. Each star's orbit is a clue, a faint echo of an invisible architecture. Dark matter is the silent skeleton of the Milky Way, shaping its form yet remaining beyond direct detection. Its role extends to galactic evolution. When smaller galaxies fall into the Milky Way, their stars are torn apart by tidal forces, but their dark matter halos merge more seamlessly, blending into the larger structure. Over billions of years, this process has built up the Milky Way's vast envelope of invisible mass. The halo is, in effect, a graveyard of past galaxies, absorbed into one grand, unseen whole. Dark matter may also explain subtle ripples in the galactic disk. As clumps of dark matter pass through, they tug on stars and gas, creating vertical waves and asymmetries. These disturbances are still visible today, evidence of invisible collisions with matter we cannot yet see. The galaxy carries these scars like wrinkles on an ancient face, silent records of encounters with ghostly structures. If dark matter holds the Milky Way together, dark energy shapes its fate. This mysterious force drives the accelerated expansion of the universe, pushing galaxies apart on the largest scales. Within the local group, gravity still dominates, binding the Milky Way, Andromeda, and their companions. But beyond, the pull of dark energy stretches space itself, ensuring that most galaxies will drift forever beyond our reach. This means that in the far future, after the Milky Way merges with Andromeda, the resulting galaxy will live in an increasingly lonely universe. As cosmic expansion accelerates, distant galaxies will recede beyond the horizon of visibility. From within Milkomeda, astronomers trillions of years from now may see only their own galaxy, unaware of the vast cosmic web that once surrounded it. Dark energy will have erased the evidence of the broader universe, isolating each galaxy in its own island of stars. The interplay of dark matter and dark energy highlights a humbling truth. Most of the Milky Way is made of things we do not understand. The stars, planets, and nebulae we admire are only the luminous frosting on an invisible cake. Roughly 85% of the galaxy's mass is dark matter, and the expansion of the universe is governed by dark energy. Our home is held together and driven forward by mysteries that remain unsolved, even as we map them with increasing precision. In this sense, the Milky Way is not only a wonder in itself, but a window into deeper questions. What is the true nature of dark matter? Is it made of undiscovered particles, or something even stranger? What is dark energy, and will it remain constant or change over time? The answers to these questions will not only reveal the destiny of the Milky Way, but also the fate of the universe itself. Long before telescopes revealed the Milky Way as a galaxy, human eyes looked upward and tried to explain its shimmering band. For ancient cultures, it was not a collection of stars, but a path, a river, or a bridge between realms. The Greeks saw it as milk spilled by the goddess Hera, giving the galaxy its name. In Norse mythology, it was the path of the slain, a road for warriors to reach Valhalla. Indigenous peoples around the world imagined it as a trail of animals, spirits, or ancestors. Each culture projected its hopes and fears into that glowing arc, turning the night sky into a cosmic storybook. With the invention of telescopes, the Milky Way transformed from myth to science. Galileo was the first to see that the band was composed of countless stars, too faint for the naked eye. Over the centuries, astronomers slowly uncovered its scale, realizing it was not the entire universe, as once thought, but only one galaxy among billions. This shift in perspective was as profound as discovering that Earth is not the center of the solar system. Each revelation has humbled us, placing our world within ever larger structures. And yet, the Milky Way remains both scientific object and source of wonder. Through instruments like Gaia, Hubble, and the James Webb Space Telescope, we map its arms, measure its stars, and probe its history. But we also still look up at it with awe, as our ancestors did, marveling at its beauty. Science has not stripped the Milky Way of its poetry. It has deepened it. Now, when we say that we are made of stardust, we know it is literally true. The atoms in our bodies once belonged to long-dead stars that lived and died in this very galaxy. The cultural importance of the Milky Way is inseparable from its physical reality. It is both a symbol of connection and a physical bridge, linking us to the rest of the cosmos. Every civilization that has gazed upon it has felt the pull of its mystery, even without knowing its nature. Today, armed with science, we can appreciate not only its beauty, but also its function, a vast system that gave us the ingredients for life and perhaps harbors countless other lives as well. In conclusion, the Milky Way is more than just our home. It is a cosmic city of stars, a cradle of worlds, a graveyard of ancient suns, and a forge where the raw materials of existence are endlessly recycled. It is shaped by visible light and invisible matter, by cycles of birth and death, by collisions and mergers, by quiet rhythms and violent outbursts. It holds within it both our history and our future, guiding the journey of our solar system as we drift through its spiral arms. One day, billions of years from now, the Milky Way will merge with Andromeda and become something new. Long after humanity is gone, long after Earth itself has vanished, the galaxy will continue its transformation, carrying forward the legacy of everything it has nurtured. But for us, here and now, it is the great backdrop of existence, the canvas upon which all of human history, and indeed all of life on Earth, has been painted. To stand beneath its glowing arc on a clear, dark night is to feel both small and infinite. Small, because we are one planet among billions. Infinite, because we are inseparably part of this grand design. The Milky Way is not out there, separate from us. It is within us, written in our bones and blood, etched in every atom. To know it is to know ourselves,